Hello, welcome once again. It's Richard and I explain. So today we are going to tackle periodic table, right? Let's just run it real quick. So when we talk about the periodic table, the idea of it developing came from a guy called Dmitri Mendeleev in 1869. During that year, in the 18s, the scientists were just trying to put up a way to develop a periodic table or some type of a pattern for the known elements. Now, Dmitri Mendeleev came up and then said that let's develop it according to the atomic weight, right? So Dmitri, and pardon me with the spellings, Dmitri Mendeleev, right? So Mendeleev in 1869 arranged the known elements at that time according to the atomic weight. And what is atomic weight? It is the weighted average of the various isotopes, right, that an element has. And when he did that, they found out that the periodic table followed the pattern, forms some type of a Lego brick, right, where if you have some elements and you put them there, you could also predict the next element that comes after. So they used that to predict it and discovered a lot more elements. Now, fast forward after that, a scientist came by the name Henry Moseley, right? Now, Henry Moseley arranged the periodic table according to the atomic number, right? Not the weight this time, the atomic number, right? Z, the number of protons in an element. So when they did that, the periodic table that we have today has been worked on over and over again. Yes, I could have bought a new periodic table. I just drew this on the board. So you better like this video, or at least you better share or watch the full video, because come on, I drew the whole periodic table on the board. So let's move on. When we tackle the periodic table, they've been arranged into rows from left to right and then column from top to down. So the rows, right, of the periodic table, the rows from left to right are called periods, right? The rows are called periods. And then the top to down, they are called groups. Now, how are the periods arranged? First, let's take groups. The groups from top to down, they are arranged according to the valence electron that an element has. So they are arranged according to the valence electron or the element's valence. That is how they arrange the group. Because of that, we have 18 groups on the periodic table. Group 1 starting from hydrogen, group 2, group 3 starting from transition elements, scandium, group 4 for titanium, group 5 for vanadium, group 6 for chromium, group 7 for manganese, group 8 for iron, group 9 for cobalt, group 10 for nickel, group 11 for copper, group 12 for zinc, group 13 for boron, group 14, group 15, group 16, group 17, and then group 18. So these are the groups that we do have on the periodic table, and that is because of the valency, the number of electrons that are in the valence shell of the atom. Now you'd say that boron, carbon, nitrogen, oxygen, fluorine do not have 18, do not have 13, 14, 15, whatever in their valence electron. But what you should put in mind that when you get to this part of the periodic table where it branches up and go that way, what you should know is that the valence electrons are basically the ones number that come here. So you do 4, 3, 5, 6, 7, and then the 8. Right? That is how it works like that. But when you talk about the transition elements or the transition metals, they are basically the exact same. Right? But what you should also notice over there is that when you get to some elements like zinc, at 12 valence shell in their electrons, because they can have a way to play around with the d orbitals, right? So let's move forward from that. When we go to the periods, right? The periods are the left to right. So the left to right, and then how are they arranged? They are arranged according to the number of shells, right? The number of shells an atom or an element has, or the principal quantum number. Because of that, the number of shells being the principal quantum number, we have 7 groups. Because all the elements that we have discovered falls within the 7th principal quantum number. If we discover a bigger, larger element, we might have the 8th quantum number. But for now, all our elements could fit in there. So because of that, we have 1, 2, 3, 4, 5, 6, 7 periods going from left to right. Right? So by so doing, that is the periodic table overview. Now, because they arrange the elements according to this criteria, the periods, the groups, and the atomic number, some elements group to itself. It's basically like, you know, what is it called? Separating by mass. You have the heavier stuff, then the less like heavier stuff comes all the way to the lighter stuff. So over here, we do have group 1 elements, group 2 elements all the way. But the elements that we do have on the periodic table falls within just 3 categories, right? So there are just 3 categories of elements that we do have on the periodic table. The first category are metals. So what distinguishes or what makes an element a metal, right? So what makes an element a metal physically? So the physical properties are 1, they are lustrous, meaning they are shiny, right? Shiny, lustrous. 2, they are malleable, right? Malleable means you can hit it, hammer it, deform it, but it won't break. They are malleable. 3, they are ductile or ductility. Ductility means you can stretch the element and it still won't break, right? If you do not reach the ductile limit, you can stretch it and it won't break. And then 4, they have high melting points, high boiling points, right? These are the properties or the physical properties of metals, right? So once we have them figured that down, and all these things, the reason why they have these properties, we will come into that when we actually get into the chemicality of it or the chemical properties. The next one that we do have are non-metals, right? Non-metals. Now, if you look at the periodic table, the metals start from group 1 and group 2, with the exception of hydrogen, sweep all the way through the transition metals, right? Those are all metals. So even if you look at the periodic table, there are more metals than non-metals on the periodic table, right? So the non-metals, they are 1, not lustrous. So not lustrous, it will become here not lustrous. They are not shiny. They are not malleable. They are not ductile. They are not good conductor of heat and electricity too. They don't conduct heat and electricity very good. They have low melting point and low boiling point. The exact opposite of metals is non-metals. Because there are a lot more metals on the periodic table than there are non-metals, all elements are compared to metals. That's why we have metals and not metals, non-metals, right? So that is how it goes. But then there are a category or some special group of elements on the periodic table that we do call them semi-metals, in between metals and what? Non-metals. We call them semi-metals or semi-metals. When you take the periodic table, just as you are about to transition into the non-metal category, there are a group of elements over there that forms a staircase pattern, right? So because of that, we draw a line over here, this line, the green line over here, right? We call it the non-metal line. We call it the semi-metal line, excuse me. We call it the semi-metal line. Why? Because it separates the metal from non-metal. And the elements right before the non-metal lines and right after the non-metal lines, with the exception of aluminium and carbon, are semi-metals. So the semi-metals we have here, they are boron, silicon, germanium, arsenic or arsenic. We have antimony, and we have polonium, right? But then antimony and polonium, they are being debated whether they are semi-metals or whether they are metals or non-metals. The reason being that doping them takes a lot more elements. Doping is the act of acting or the process of adding impurities to a semi-metal to make it conduct more, to increase its electrical conductivity. That is doping. Doping it is a little bit skeptical, so that is why scientists are still debating whether these two are semi-metals. So once we have them like that, we are going to move on, right, onto the periodic properties, right? The periodic properties. Periodic properties. The first periodic properties that we're going to talk about is ionization energy. I believe you have heard of this before, ionization energy. When we talk about ionization energy, what we talk about is the energy. It's the energy required to add one electron to a gaseous atom. The energy required to add what? One electron to a gaseous atom. So if you have an atom here, let's not take lithium for instance. If you have lithium, right, and then you go lithium atomic number 3 has one electron, and then one here, right? The energy required to add one more electron to this lithium atom in its gaseous state is what we call ionization energy, right? And as it stands right now, what is the trend of ionization energy on the periodic table? See, we are adding one electron into an atom, right? So what will be the factors that would affect us adding electron into the atom? But before that, before we even talk about adding electrons into the atom, let's talk about something over here. Let's first talk about some 3 rules that I want you to follow. Effective nuclear charge, right? ZF. Effective nuclear charge, it is the net positive charge. The net positive charge that an atom exerts on its valence electron. The net positive charge. The reason why it is the net positive charge is that when this nucleus is trying to exert an charge onto this, because it's positive, it's negative, trying to exert the electrostatic force to attract it, the ones that become effective is what we call the effective nuclear charge, represented by ZF, right? Z effective, right? And it depends on how far the atom is from the nucleus of the atom. The farther you go, the less effective the nuclear charge becomes. The more you are closer, the more effective the nuclear charge is. And then also your other brother electrons in here. If the other brother electrons in here repel you, they take some of the effective nuclear charge too. So, or the nuclear charge. That is why what gets into you is called effective. Because it's not all the charges that the nucleus has is what you get. You get what is effective to you after your brothers have taken, your other electrons have taken their share. So once we have that, let's move on. The second rule is that atoms will gain or lose electron to form a stable octet. Right? Atoms will rather gain or lose electrons to form a stable octet. The reason being that every atom wanna, the octet is kind of rule of thumb, right? Rule of thumb. Say like they obey the rule whether if it's convenient for them, then they do obey the rule, because there are a lot of elements. In fact, there are more elements that do not obey the octet rule than there are elements that obeys the octet rule. So, but then one rule of periodic chemistry is that atoms will rather gain or lose electrons to form a stable octet. Once we have these 2 rules over there, let's move on to the periodic table. So as I said earlier, the atoms would wanna what? Gain. You wanna for the ionization energy, you wanna add electron to the gaseous atom. Now, the effective nuclear charge over here would make it hard to add an electron, because let's say you are adding one more electron. This is the electron that you are trying to add. It already has 3 electrons. If you add it, the 3 electrons are going to repel it. That is first. And also, the charge on it is going to be less, right? So imagine us going down this group. And we say the more down of the group we go, the more shells we do add. So let's say for this lithium, atom. If we descend down to sodium, we add one more shell. If we descend down to potassium, we add one more shell, pushing the valence electron or electron that we're going to add further and further away, right, from the charge, right, from the effective nuclear charge. So if we want to add electron onto this electron, or for the ionization energy, if we want to add the electron, we are going to need a tremendous amount of energy the more we go down the group, because the more we go down the group, the more shells we add, the more the repulsion becomes, the more energy we need to overcome that repulsion, right? The electron repulsion. So as we go down, ionization energy is going to what? Decrease. That is literally how it is. And as we go across the period, as we go from left to right across the period, we don't skip shells, right? We don't add shells, rather we add protons. That is why it is arranged according to proton number or atomic number. We add protons as we move from left to right across the period. So if we add in a proton number using the same element over here, right? If we are adding protons as we come across, or as we go across the group, the nucleus is getting bigger because we keep on adding protons. Protons live in the nucleus, so it's getting bigger. And the bigger it gets, the more effective nuclear charge it can give out, the more it is becoming stronger to hold the electron. So as it's becoming stronger to hold the electron, we do not need a tremendous amount of energy to put the electron as we go what? From left to right across the period. So ionization energy rather decrease as we go across the period, because no electrons are being added but rather protons, and we are increasing our effective nuclear charge, therefore grabbing the electron and putting it in place. Okay, so that is ionization energy for you. The next one that I want to talk about is electronegativity, right? Electronegativity. Now, electronegativity, right? Pay attention right here. Let's discuss it in 3 minutes. Electronegativity is the amount of force. See, this in this case, not energy. Is the amount of force an atom would exert on an electron if it comes into proximity with it. So more or less, it is more prevalent in covalent bonding, because that is where electrons are shared. It is where it is the force that an atom would grab onto an electron that comes into proximity. So as soon as the atom sees electrons, the force that it used to grab it is the electronegativity, right? So as I'm grabbing the electrons onto me, if I am an atom, and I'm grabbing the electrons to me, how much force I'm going to use to grab the electron depends on my needs, if I need electron or not. If I do not need electron, I wouldn't be, forcing myself to grab the electron. But if I really do need this electron to be stable, I'm going to grab onto it real quick that my fellow or my colleague element would, or my colleague atom would. So as we take the atoms over here, right, the atoms that really want to lose electrons to form a stable octet, like if you write the electron configuration of the atom, you will see ones that want to lose electrons to form stable octets, and they are basically metals, right? So since they are basically metals, the force that they are going to use to get the electron is less, because they don't need it. In fact, they have an electron they want to get rid of. Why would they need an electron? Or why would they exert more force getting an electron from somewhere? So that is why we have electrons here, right? All right, I have class. So with that being said, let's see the trend of electronegativity on our beautiful periodic table over here. As I told you once again, better like this video, man. Better like it, because I drew the periodic table on board freestyle. Better like it. So, for the electronegativity, if it is the energy that an atom would exert on an electron, if it comes into proximity with it, then it also have a tie with electron with the ionization energy because the ionization energy is adding the electron onto the atom. If that is the case, then the more down we go in the group, going from top to down, the electronegativity values would what? The force that an atom would exert on an electron would what? It will decrease, because as we go, the atoms what? Add more electrons and add more shells. They have an abundance of electrons and shells, right? So the energy the atom is going to exert, and the force is going to be what? Low as we go down this group. And then as we go across the group, the energy is going to what? Increase, because as we go down here, protons are being added, which means it is making the atom wanna get electrons more. So as we go across the period, the electronegativity values are going to what? Increase. The next one that I want to tackle is electron affinity. Now, electron affinity is very similar to electronegativity in a sense that they are all adding an electron into an atom, so it's similar to ionization energy. But in this case, it is the energy the atom is going to release, right? It is the change in energy, or the energy the atom is going to release as you add 1 mole of it, as you add 1 mole of electron, or as you add electron onto the atom. So electron affinity is an energy actually that the atom will release as you add electrons onto it. So how much energy the atom will release would base on how it wants electron or not. If it wants more electron, it will release more energy, meaning it is excited and happy. If it does not want electron, it will release less energy. Because, bro, why are you giving me an electron? I already have a lot. In fact, I have some I want to get rid of. So why are you giving me more? So let's look at the trend of electron affinity on the periodic table. So the trend of electron affinity on the periodic table is that as you go down the group, as we are going down the group, the energy that the electron is going to release will get less and less. It will get lower and lower because they already have electrons. They already have abundance of shells and electrons. Why would they want more electrons? So they will release less energy in effect. So they decrease down the group. So it decreases down the group. Down the group. And as we go across the period from left to right, it increases due to the same phenomenon or the same mechanism, right? That's the electron, the electronegativity and the ionization energy high, because there are more protons being added, which makes the atom want to get electrons more or have the energy to hold onto electrons, thereby will release more energy. So if we take a look at all these three, right, like all these three, electron affinity, electronegativity, ionization energy, like all these trends, all these properties have just one trend. All these properties, they all decrease as you go down the group, and they all increase as you go down the period, right? So that is how it is. Electron negativity, affinity, ionization energy, they all have the same trend. So just memorize one for all of them. That's how it works. But the trend that makes a different, that brings a different, the property that brings a different trend is the atomic size. Now, when we say atomic size, right, it is the size or it is the distance between the centers of two atoms held adjacent to each other. So if you take an atom like this, right, and we tell you to describe its atomic size or weigh its atomic radius. Let's use atomic radius for instance. You cannot just pick one atom and measure it as if you are doing it for a circle. The reason behind this is that atoms don't look like this, right? Atoms are just a dense nucleus with clouds. Inside the clouds, that is where you have the chance of finding an electron. So it is not a regular circle like this. In the real world, an atom is not a regular circle. We draw it a regular circle to do what? To make it easier for us. So if you want to measure an atom, you bring an atom of the same element in close proximity to each other. So let's say this is a hydrogen atom. We bring another hydrogen atom in close proximity to each other, right? The atomic size will be the distance between these two centers, right? Here to here, divided by 2. So let's say this distance is d. So the atomic radius, let me see, a radius, right, will be this distance, or the d, from one center of an atom to the center of another atom held adjacent to each other, divided by 2. That will be the atomic radius. Now, atomic radius, on the other hand, have a different trend. The reason why it has a different trend is that as you go down this group, as you descend down this group, you add shells, right? So if I started with hydrogen, right, and I know most of you know this trend already, but if you started with hydrogen, which has just one electron, let's say orbiting somewhere around here, and you move on to lithium, which has 2 electrons, I move here, and then I add hydrogen, it will get like this. If I move on to sodium, see, one more shell. If I move on to potassium, another shell, right? If I move on to rubidium, and then cesium, and then francium, I keep on adding shells. So it gets bigger. The atom gets bigger as I go down this trend. It gets bigger as I go down the trend, down here. So that is why atomic radius would increase as you go down the groups like this. It increases. Doesn't matter which group you take. It will increase as you go down the group. But as you go across the period, it decreases. The reason why it decreases as you go across the period is that let's start with lithium. Let's leave here with lithium. Now lithium has 3 electrons, right? Let's say it looks like this. If we go from lithium to beryllium, right, we do not add more shells. We basically add just one electron. If we move from beryllium to boron, say we add one more electron, and then we keep on adding protons too, because as we go across the period, we add protons. If we go to carbon, we add another 1 electron, nitrogen, 1 electron. So you see, it is same shell that the electrons are being added onto it, and protons are being added also to counteract. So therefore, it is the same size, but more protons. So the cell actually, the atom actually gets smaller, right, as you move across the period. So for atomic radius, it gets smaller as you move across the period. Now let's talk about ionic radius. Ionic radius is when the atoms have become ionized. That is a little bit different from this, and it requires a little bit of critical thinking, because it doesn't have a specific trend that is followed. It depends on the atom that you are analyzing, right? Because some atom will form cations and some will form anions. So if the atom is gaining electron, by so doing, in logical sense, the atom should have a bigger radius. The ion of that atom should have a bigger radius. Let's take fluorine, for instance, right? Other fluoride. Fluoride is the 9th. Fluorine over here is the 9th atom. Right, so let's draw fluorine. A fluorine with a good nucleus. Right, let me use a different pen marker. So fluorine has this nucleus 2. Go over here, this marker even worse. Why can't I find a marker that is a virgin, that has not been used? Oh, my markers have been in the streets. Let's take fluorine, for instance, right, has 2 electrons over here, two more, making it 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, like this. Say fluorine has this electron configuration, right? Now, for fluorine to move to gain 1 electron and move to fluorine minus, I will have to put 1 more electron here, right, to become this stable, right? In effect, since we just added 1 electron and we did not counteract with a proton, that there will be like a net negative charge that will expand the atom. So in that case, fluorine ion would be bigger than the fluorine atom because we added 1 electron and did not counteract with the proton, so thereby expanding the radius. If we take sodium, also for instance, sodium is the 11th atom, right? So let's say fluorine, we're gonna get 1 more shell. This is 10 fluorine. So the sodium is like this, right? If sodium wants to become an ion, it has to lose this 1 electron to achieve what again is stable octet. Now if sodium loses this 1 electron, you erase the shell, right? Thereby reducing the size of sodium, and sodium will become a positive charge. So if you are saying we are comparing what is the ionic radius of sodium compared to the regular fluorine size, they pretty much equal. Or if you think about it, then you have to count the number of protons in it. The number of protons will determine how big it is. If the fluorine protons exceed these electrons, you think about it logically. If the same thing applies to sodium, you think about it logically also. So that is how you go about the specific periodic properties, right? So as we draw it like this, we draw its electronegativity, ionization energy, electron affinity, and then atomic radius, and then ionic radius, right? If we do it like this, and then we say the trend across the group and down, across the periods and down the group, period. Oh wow, this is nice. Period, and then groups. The trend, how is it going to go? So for ionization energy, we say if we go across the period like this, it will what? Increase. So it increases. And then it will decrease down the group. Same thing applied to this, same thing like this, like that. But when we get to ionization energy, atomic radius, it is different. It's like this and then like that. And over here, ionic radius, for that you have to think logically. So that is how the periodic properties work. Now that we found the periodic properties, let's talk about each individual groups on the periodic table. So the group 1 on the periodic table, they are called alkaline earth metals, right? Alkaline or alkali earth metals. Alkali metals. And then the group 2 are alkali earth metals, right? The alkali metals and then the alkaline earth metals are some of the most reactive substances on the planet, right? Because they have this one, the first one, the alkali metals have just 1 outermost electron to lose. They will do anything to lose that electron. So it is reactive to the extent that it will even react with light if you just leave it by itself. So they are reactive in such a way that they are not even stored by themselves in lab. They are stored in non-reactive fluids like paraffins, right? So because they are so reactive and they want to lose 1 electron, you don't really find them in nature by themselves. You mostly find them in nature reacting with these group 7 or group 17 elements, right? Because they will lose that 1 electron, and this one will pick it up because they need 1 electron to form a stable octet like our noble gases over here. Same thing happened to group 2 metals, right? The group 2 alkali earth metals, right? You will also see them not by themselves in nature. In fact, what is it called? They would also form bonds with other chemical, other elements on the periodic table because they are that highly reactive. Now, when we come here, right? So this, when we was doing the orbitals and then the atomic whatever, this was called the S block, right? And then the P block and then the D block. When we come to the D block, this block D, right, of transition metals, for them, they are a bit tricky because they can form many oxidation states, meaning they can either lose or gain electrons depending on the elements that they are reacting with, right? So if they are reacting with elements over there, they tend to gain or lose electron based on that because they have d orbitals. And you know the d orbitals have 5, the d sub shell have 5 different orbitals. So with these different orbitals, if each of them is filled individually or whatever way that they are filled, they could tend to lose some amount of electrons here and also gain some amount of electrons here, right, to still involved in stability. So that is the transition metals over here. The lanthanides and the actinides, they go here in the periodic table also. They are put down here for 2 reasons, because of aesthetics, because if we're supposed to put them here, there will be a wide gap on the periodic table and printing it will be harsh. We also put them down here because they don't follow a trend, right? They are so unpredictable in nature that they don't follow no trend. You cannot say since scandium, yttrium, I believe so, it's yttrium. Since scandium and yttrium are following a particular trend, you cannot say the lanthanide and the actinide that falls below them follow the same trend. It goes throughout the periodic table, so that's why we also put them down here. Now that we're done with the alkali metals and then the alkaline earth metals, let's move on to our semi-metals, right? That goes here. We talked about it, so we're not really going to talk about it anymore. So the group with a carbon in it, right? This group falls in the semi-metals, and this group with nitrogen in it also have semi-metals and some non-metals over here. But group 16, right? We call them chalcogens. Chalcogens. That is what they are called. Chalcogens. Chalcogens because they are some of the biologically important elements, right? They are really needed for life to sustain. Oxygen, sulfur, selenium, tellurium, polonium. You don't know what that is. LV. Put it in. Is it Louis Vuitton? I don't think so. So yeah, that is how it goes. But a lot of these, even though they are very important for biological life, if they come in excess, they are also toxic, right? So you would see like if you have too much oxygen, you're gonna have hyperoxemia, which is not good. Same thing. And then the group 17, they are called halogens, right? Halogens. Halogens, not Halloween, halogens. Halogens, they are also very reactive, but not as reactive compared to the group 1 and group 2 elements. Because of that, they are usually found in diatomic gases, right? Like fluorine will be like, you see fluorine in nature as F2 gas, a chlorine 2 gas, a bromine 2 gas, an iodine 2 gas. The diatomic molecules that they form are called halides, right? So that's why you find them mostly like that in nature. And then we come to our almighty noble gas. Almighty noble gas don't react. In fact, they have little reactivity. Helium will do some type of reaction, maybe a little bit with neon, but for the rest, they don't really react. They are just there. That is why their electronegativity values are non-detectable, almost 0. Now, there is a scale that we use to measure electronegativity because it is the force an atom would exert on an element, and it's in comparison as to other elements because it is in covalent bonding, and covalent bonding are usually between 2 elements, right? So the skills that we do use, the standard skills, they call it the Pauling electronegativity scale. Pauling, so the Pauling EN scale. And then it is a scale that starts from 0. I think it's 0.7 all the way to 4. Right? So the lower you score on the Pauling electronegativity scale, then that means you don't want electrons. The higher you score up to that 4 number means you want more electrons in your bonding. So this right here is what we call periodic table. Now a quick refresher. The periodic table, the idea came in 1969 by a Russian scientist called Dmitry Mendeleev. It was worked upon by Henry Moseley, and after that has been worked upon. Mendeleev arranged it according to atomic weight. Henry Moseley also did it according to the atomic numbers, and they arranged it into groups and periods. The period is from your left to right and is done based on the atomic numbers or increasing proton numbers. The groups which is top to down were arranged according to your increasing quantum numbers or the number of shells that you do add on it. There are 18 groups on the periodic table from group 1 all the way to group 18. From group 3 to group 12 are what we call transition metals. The group 1s are called alkali metals. They are very reactive, and therefore then you cannot find them in nature. They will react with the group 17 elements in nature. And then also the group 2 elements are also very reactive. So you find them also in reaction with other elements on the periodic table. Lantanides and actinides do not go here because it makes the periodic table too big, and they don't also follow any trend. Also, when you come here to the our semi-metals over here, they are found between, they have both metallic and non-metallic properties. They have a lot of uses, like the semi-metals, especially silicon in your phones are usually made of semi-metals over there. And we have some biologically important elements like carbon, oxygen, sulfur, selenium, tellurium. The group 16 elements are called chalcogens because they are biologically important. Too much of them is bad though. Group 17 elements are called halogens because they are reactive. They are usually formed in diatomic molecules called halides by themselves. The group 18 elements are non-reactive. They are called noble gases. That is helium, neon, argon, krypton, xenon, radon. I don't know what that last one is. And we talk about the trends. First of all, we talk about ionization energy. We said it decreases down the group and increases across the period because the atom, as it goes down the group, more shells are added, and as you go across the group, more protons are added. We also talk about electronegativity, and we also say that one decreases down the group and increases across the period. We also talk about electron affinity, and we also say that has the same trend as the first two. It decreases as you go down the group, and then it increases as you go across the period. But then the breaking point to the trends was the atomic radius. That will say it will increase down the group and it will decrease across the period. And we say ionic radius is more technical because we have to think about it logically to say that. And we say we measure electronegativity using Pauling's electronegativity scale. So that is the periodic table and periodic properties. Our next topic is going to be bonding, whereby the periodic table here and what we have discussed will be very important as to which atom bonds to which atom would likely form bonds with other atoms. And we'll talk about the type of bond, ionic covalence, metallic bonds, and stuff like that. Thank you very much. My name is Richard. Please like and share this video. See you in the next one. Bye.